This is a video from section 16.3. This is in a Calculus 3 class. Determine whether or not f is conservative. If it is, find a function small f such that capital F is equal to the gradient of some small f. So we're going to look at problem 3, and problem 3 says capital F of xy is the quantity xy plus y squared times I plus the quantity x squared plus 2xy times j. This is how we determine whether or not you have a conservative vector field. I'm going to let p of xy equal xy plus y squared. The partial of p with respect to y, and remember when you take the partial of p with respect to y, x is constant. So I'm going to get x times 1 plus 2y. Okay? And I'm going to let q of xy equal x squared plus 2xy. And I'm going to take the partial of q with respect to x. And when I take the partial of q with respect to x, that means y is constant. So I'm going to get 2x plus 2x multiplied by 1, which is equal to 4x. Now, notice, since the partial of p with respect to y is not the partial of q with respect to x, we can conclude that f is not a conservative vector field. And that's how you do problem number 3. If we take a look at problem number 4, suppose f of xy is y squared minus 2x, this quantity times I, plus 2xyj. So I'm going to let p of xy equal y squared minus 2x, so essentially the first component. And I'm going to let q of xy equal 2xy. So the partial of p with respect to y, so remember when you take the partial of a function with respect to y, x is constant, right, for this particular scenario. And so this is 2y, and the partial of q with respect to x is going to be 2y. Well, that's good. Since the partial of p with respect to y equals the partial of q with respect to x, we can say f is a conservative vector field. So the question is, what do you do from there? Now, to find what's called the potential function f, and when I say f, I want the small f. This is what you do. First, I'm going to set the partial of f with respect to x equal to the first component, and the first component is y squared minus 2x. Now, second, we want to find f of xy. Now, here's the deal. One thing I want you to note, if we go back to step 1, it's the derivative with respect to x. And what that tells me is because you're differentiating with respect to x, y is constant. okay? So when I want f of xy, I'm going to get xy squared. And how am I doing that? I'm integrating with respect to x, okay? I'm going to subtract x squared. Now, you have to add a constant of integration. It's not enough to add k, because remember that y is constant. And if y is constant, y squared is constant, y cubed is constant, sine of y is constant, cosine of y is constant, y squared plus 2y minus 3 is constant. And so to capture all of those constants, what I'm going to do is I'm going to add some function of y. That captures numbers and any term that has a y in it. Okay? So we have to add g of y. Third step. So what I'm going to do is I'm going to find the partial of f with respect to y. So you notice I integrate and then I'm going to differentiate again. Okay? And I would flip-flop back and forth if there's an additional component. So the partial of f with respect to y is equal to the following. You're going to get 2xy. This term goes away because, remember, x is constant. So I'm going to get 2xy plus g prime of y. Now, let's go back. I'm going to use the second component to get a handle on g prime of y. So on the fourth step, I'm going to set 2xy plus g prime of y equal to 2xy. But that says g prime of y equals 0, and that says g of y equals k. And so I'm done. What this says is f of xy equals, you're going to get xy squared minus x squared plus k. And that's my potential function. Now, what's a way to check? If I take the partial of f with respect to x, I should get the first component. So in other words, if I take the partial of f with respect to x, I should come up with this first component. If I take the partial of f with respect to y, I should get the second component. So notice if I take the partial of f with respect to x, I get y squared minus 2x. And that's exactly what I'm supposed to get. If I take the partial of this function with respect to with respect to y, I get 2xy. And that's exactly what the second component should have been. So this here is my what's called potential function. Okay? And that's number 4. Let's go ahead and take a look at number 5. Suppose f of xy equals, I'm going to get y squared e to the xy times I plus 1 plus xy times e to the xy times j. Okay, so let p of xy equal y squared e to the xy. And I'm going to let q of xy, just give myself a little room, equal 1 plus xy times e to the xy. So I'm going to take the partial of p with respect to y. And since each factor has a y in it, I have to apply the product rule. So I'm going to take the derivative of the first function, which is 2y, and I'm going to multiply by e to the xy. And I'm going to add. And then I'm going to take y squared and multiply by the derivative of the second function, which is going to be, by the chain rule, I get e to the xy times the derivative of xy, which is going to be, in this case, x. So we should get something like this. Now, if I factor out a ye to the xy, I get 2 plus xy. Now, if I take the partial of q with respect to x, I'm going to take the derivative of the first function with respect to x, which is going to be y, times e to the xy, plus 1 plus xy e to the xy. So derivative of the first times the second plus the first times the derivative. Oh, and then by the chain rule, I'm going to multiply by y. And so if I factor out a ye to the xy, I'm going to get 1 plus xy, right? But this is ye to the xy times 2 plus xy. So it does turn out, since the partial of p with respect to y is the partial of q with respect to x, f is a conservative vector field. Now, to find a potential function f, this is what we do. Now, first, we're going to set the partial of f with respect to x equal to y squared e to the xy. Okay? And that's the first component. Now, remember here, one thing to keep note of always is what's constant. In this case, y is constant. So it's not so bad, believe it or not, because f of xy is going to be the following. Now, remember, y is constant, so I claim you end up getting this. You get ye to the xy, right? But remember, y is constant, so we have to add some function of y. Just like this. Now, in the third step, I need to find the partial of f with respect to y. But when I find the partial of f with respect to y, and by the way, the reason why I'm doing that is because I'm going to use the second component to get a handle on this. Remember, you're trying to find the gradient, and the gradient is it's a vector comprised of the partials, right? And so here, I'm going to take the derivative of the first function, which is 1 times e to the xy plus y times the derivative of e to the xy with respect to y, which is xe to the xy, plus g prime of y. And I'm going to say the partial of f with respect to y is e to the xy times 1 plus xy plus g prime of y. Now, I'm going to set e to the xy times 1 plus xy plus g prime of y equal to the second component, which is e to the xy times 1 plus xy. And so that says g prime of y equals 0. And so remember, that second component is over here. It's right here. And so that says g of y equals k. And that's exactly what I wanted. So I needed to get a handle on that g. And that allows me to get my potential function. So I get y e to the xy plus k. And that's exactly how you do problem number 5. Let's take a look at problem number 7. Suppose f of xy equals, we're going to go y e to the x plus sine of y times I plus e to the x plus x times cosine y times j. The hardest thing in the world is to just keep track of your variables, you know. So if I let p of xy equal y e to the x plus sine of y, I'm going to do the partial of p with respect to y, and I'm going to get e to the x plus cosine of y. And I'm going to take q of xy and set it equal to e to the x plus x times cosine of y. And then notice how that's the second component over here. So if I take the partial, I get e to the x plus cosine of y. Since the partial of p with respect to y is the partial of q with respect to x, f is a conservative vector field. Now, to find that small f, same game. First, I'm going to set the partial of f with respect to x. That's the first component of that gradient, okay? Now, that's going to be y e to the x plus sine of y. Now, I always want to remind myself y is constant. Always keep track of what's constant. Now, second, f of xy is y e to the x plus x sine of y. But remember, y is constant, so we have to add that function of y. Third, if I take the partial of f with respect to y, I get e to the x plus x cosine of y plus g prime of y. Notice I set the partial of f with respect to x to be the first component. I integrate, but I make sure to remember that y is constant. Then I'm going to differentiate, and then what I'm going to do is I'm going to set, let's go back, e to the x plus x cosine y plus g prime of y. I'm going to set that equal to e to the x plus x cosine y. That says g prime of y equals 0. And a common question is that always going to be true that g prime of y is 0? The answer is no. No, it just happens the problems that have been selected so far have resulted in that. And so g of y equals k. And so that implies f of xy, my potential function is y e to the x plus x sine y plus k. Yep, and that would be my potential function. And that's a pretty good stopping point. That concludes this video for section 16.3. We worked on problems 3, 4, 5, and 7. Okay, thank you.